Right, so in the first two sections of chapter 13, we used the first derivative to help us figure out when a function was increasing, decreasing, where it has a relative max or a relative min. Now let's talk about what happens if we take the derivative of the derivative, or what we call the second derivative. We're going to use the second derivative to help us find other characteristics of a graph. So it says here higher derivatives are derivatives of derivatives. A function f has a derivative f prime, then the derivative f prime, if it exists, is the second derivative of f, written f double prime. The derivative of f double prime, if it exists, is called the third derivative, and so on. So we can continue to find derivatives by just taking the derivative of the function before. So let's say our original function was f of x if f of x was equal to x to the fourth plus 2x cubed plus 3x squared minus 5x plus 7. The first derivative, with that proper notation, because now if we're going to continue to find derivatives, we have to notate them in a special way so we know which one is the first derivative and the second derivative, and so on. My first derivative would be 4x cubed plus 6x squared plus 6x minus 5. But what if I wanted to take the derivative of that function, the second derivative? Well, the second derivative then would be 12x squared plus 12x plus 6. I can even find the third derivative, 24x plus 12. I can even find the fourth derivative of 24. I can even find the fifth derivative. What would the fifth derivative be? 0, right? And so I can continue to find derivatives over and over and over again until I need to stop or they ask me to stop. So we have a couple different new notations now when we talk about higher derivatives. So for example, if we have the second derivative, a couple different notations would be kind of like the f prime, but in this case it would be f double prime. I could find the second derivative of y with respect to x. I can find the second derivative of f of x with respect to x. The third derivative can be written in the similar way, but anything typically from the fourth derivative on, we write it with a special parentheses around the exponent, so the fourth power, fifth power, and so on, kind of like we did up here, okay, to find the nth derivative. So let's do a few examples where we're finding higher order derivatives. So in example number 1, it gives us f of x as x cubed plus 6x squared minus 9x plus 8. And it asks us to find the second derivative. Now, obviously, before we find the second derivative, we have to find the first derivative. So what would the first derivative be of f? Again, with proper notation, hopefully you've labeled it just like I have, you should get that the first derivative is 3x squared plus 12x minus 9. Now we have to find the derivative again. Let's label it the second derivative, f double prime. The second derivative would be 6x plus 12. Now part B asks us to find the second derivative when x is 0. So using our second derivative over here, let's figure out what the value of my second derivative is when x is 0. If I plug in a 0, I end up getting that the second derivative at x equals 0 is 12. Let's do another one. These ones are a little more complicated, right? They can't always be so easy. Example number 2 asks us to find the second derivative for the functions defined below. So our first function is the quantity x squared minus 1 squared. So we've got to find the second derivative, but before we find the second derivative, we've got to find the first derivative. Now look at that carefully. What derivative rule will you have to use in order to find the derivative of f? That's a chain rule. Hopefully you saw that. Where you bring the 2 forward, you keep the inside the same, you subtract 1 from the exponent, so your new exponent is 1. You can write it or not. And then don't forget to make sure that you multiply by the derivative of the inside, so the 2x. Combining some of my like terms, I can put the 2 and the 2x together, calling it a 4x times my x squared minus 1. I can even distribute the 4x through and say that my first derivative is 4x cubed minus 4x. You've noticed that I've continued my good notation because all of these expressions or functions are still my first derivative, right? But they asked me for the second derivative. So now that I have the derivative written in as nice of form as possible, that's why I didn't stop here or here. I tried to make it look as nice as possible because I knew that I was going to take the derivative again. We always want to try to simplify as much as we can so it gives us less work to do later. Now let's find the derivative of my first derivative. You should end up getting 12x squared minus 4. All right, let's look at b. b gives us a function, g of x, and it says here that we have a 4x times the natural log of x. Hopefully you saw that we have two functions, two things with variables that are being multiplied together. So what derivative rules will we have to use here? Well, this looks like a product rule, and within that product rule, hopefully you remember what the natural log derivative rules are also. Product rule says the first, which is our 4x, times the derivative of the second. And do you remember what the derivative of natural log of x is? Hopefully, the derivative of any natural log, remember, is the derivative of the inside over the inside. So the derivative of x, which is 1, over the original inside, which is just x. So I have the first times the derivative of the second, plus the second times the derivative of the first, and the derivative of 4x would just be a 4. You might notice here on the 4x, you can put it over 1. That means the x in the numerator and the x in the denominator reduce each other, and so I'm just left with a 4 plus 4 times the natural log of x. Being careful not to put the 4 and the x together. The 4 is really a coefficient, a value that you're going to multiply after figuring out what natural log of x is. So in order to not get confused, I always put that 4 in the front of the natural log of x. Now those are not like terms. I can't make that an 8 natural log of x. I would just leave it just the way it is. But remember, that's still just the first derivative, and I still have to find the second derivative. So let's find the derivative again. The derivative of 4, the derivative of any constant, remember, is just 0. On this term, I should be able to keep my coefficient, the 4, there. It's just a number in front. And then just find the derivative of the rest of my function. You should not have to use product rule on that one because the 4 doesn't have a variable with it like it did in my original problem. It is just a coefficient, just a number in the front that I can leave out in front, and then just find the derivative of natural log of x, which is 1 over x. I can simplify my final answer and say that the second derivative of g double prime, is 4 over x. All right, let's do one other one in this video where we're finding this second derivative. Look at this one. This one also has multiple derivative rules in it. Hopefully you have remembered all of your derivative rules from last chapter. What derivative rules do you think we'll use in this one? It looks like this is a quotient rule. I have a variable in the numerator and denominator, two functions being divided. So I have got to use quotient rule. And it looks like I need to make sure that I apply the exponential derivative rule. That one's kind of easy, right? That one should be the easiest one. Do you remember the derivative of e to the x is just e to the x? All right, so here we go. Quotient rule says the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So yours should look something like mine. In my numerator, I can simplify a little bit. I have e to the x minus x times e to the x all over e to the x squared. I noticed that in my numerator, both terms had an e to the x, so we can GCF out that e to the x, leaving me with a 1 minus x in the top over my e to the x squared on the bottom. You might also notice that I have an e to the x. That's a common factor in my numerator and in my denominator. So I can reduce an e to the x in the top, and I can reduce one of the e to the x's in the denominator. So I'll have one more left over. That means my final first derivative is 1 minus x over e to the x. Whew, all that work, but guess what? That's just the first derivative. We still have to find the second derivative. So let's now take the derivative of h prime. That looks like another quotient rule. That's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. What'd you get? Hopefully you got the same thing I did. When I simplify the numerator, I ended up getting negative e to the x. What I also did is I distributed the e to the x and the negative 1, or a negative e to the x. That gave me another negative e to the x plus x e to the x. You might have noticed that these are like terms. I have a negative 1 e to the x and another negative 1 e to the x. So that's a negative 2 e to the x. And all terms had an e to the x, so I factored out an e to the x. That left me with a negative 2 plus x. Don't just follow what I have here. Make sure you're working it out so you understand where I got those numbers from. So you might want to pause the video and work this out on your own to make sure you got the same answers that I do. I'm going to go ahead and reduce again the e to the x on the top with one of the e to the x's on the bottom. That left me with a final second derivative of -2 plus x over e to the x. So making sure you know all your derivative rules, and you can practice by taking not only first derivatives, but now second derivatives and even third derivatives and even fourth derivatives and so on.